Okay, guys. So if I were to survey the high school student body and ask them what is one of the main concepts that they've struggled with or that they find very abstract and confusing mathematically, I think probability is going to be up at the top of that list. Okay, and I think probability is a hard concept for people to understand because, one, they don't pay attention to what the sample space is, or they don't have a good way of visualizing what the sample space is. It's kind of like if you're in science class, you guys deal with maybe like sound waves or gravity or inertia or momentum. Those are things that you cannot physically see, right? We can maybe recognize or see the impact of gravity. It keeps me stuck to the ground, right? But I can't actually see the force gravity, okay? Maybe I can see inertia and momentum on an object, but I can't actually see the force. Does that make sense? Okay? Likewise, I can interpret sound waves. I can talk about their frequency, their duration, their amplitude, that kind of stuff, but I can't see a sound wave. Does that make sense? It's invisible, all right? Same thing with other like electromagnetic waves and that kind of stuff. So there's things in science and math that you cannot really visualize that I think makes it difficult to discuss and analyze. I think probability is one of those things, okay, or is very similar to that. But we do have ways of helping fix that idea, fix that issue, and that's to make sure that we have a full understanding of what our sample spaces are, okay? Now, every scenario is a little bit different. Some scenarios, the sample space will be explicit. It'll be provided for you. These are maybe the people that we have researched, that we've surveyed. These are maybe this is the control group of this research project. So you know that you're choosing out of 50 people, 50 random people, 100 people, whatever, okay? So they'll tell you what your sample space is. Other times it's really vague. For instance, when we look at this first one here, it says a sample space, first of all, is a set of all possible outcomes of a probability experiment, okay? All possible outcomes. So my first probability experiment here, and you don't have this picture, I added this after I sent out the email, but the sample space, if I just look at this phrase, sample space example of rolling 2 dice, we can roll on the first roll. Give me a number that we could come up with on the first roll. Not a 7. 5. Okay? Rolling dice, right? 6 sides. So you can't have 7. So I've got 5. What could come up on the second roll? Okay, 3 would be okay. So that's one of my objects in my sample space. Okay? Now, if I roll my dice again, what is something that could come up again on the first roll? Okay, I heard 3, and I heard 6. So I got a 3 on the first roll and 6 on the second roll, right? That's logical. That makes sense. Give me another first roll. 1, and the second roll could be a 1. I heard that. Okay? What's another first roll? 2. What's the second roll then? Okay, I heard 2 again. I heard a 2 and a 5. Okay? And those are all parts of my sample space, right? But as I list them this way, and we're just kind of grasping out of thin air a first roll and a second roll, there's a chance that I might miss an object that needs to be in my sample space, an outcome that needs to be in my sample space. There might even be a situation where I accidentally, as I write these out, because I don't have a systematic way of doing it right now, I might accidentally rewrite 3, 6 again later, where now I've incorporated the same outcome 2 times, so now that outcome is no longer equally likely to occur, and that's a problem with probability. So when we structure a sample space, there are times where developing a table is going to be important to us. This is the way that we would structure that table for rolling 2 dice. Okay? The top row, the 1, 2, 3, 4, 5, 6 that is red, would be representative of our first roll. Okay? The yellow column then is our second roll. And these ordered pairs then are saying, so 1, 1 is that roll there, followed by that roll. 2, 1 is that roll, followed again by that roll. Does that make sense? Then we go 3 followed by a 1, a 4 followed by a 1, a 5 by 1, 6 by 1. And that takes care of every situation in which our second rule was a 1, right? Does that make sense? Okay, if you look at it going up and down the columns, it might make more sense to do it looking at the columns. That column is every single situation, every single outcome in which the first rule was a 1. And then it's paired with a 1, a 2, a 3, a 4, a 5, and a 6 for the second rule, right? The next column addresses the situation where our first rule was a 2, and then our second rule could be a 1, 2, 3, 4, 5, or 6 with it, right? And we can systematically kind of do that. Well, if our our first rule was a 3, followed by a 1, 2, 3, 4, 5, or 6, and so forth all the way through, right? That kind of makes sense? That way is more systematic to develop a sample space, to understand and visualize the sample space, because it guarantees that I don't leave any out. I don't accidentally maybe leave 4, 6 out, or accidentally leave 6, 5 out. And it eliminates the potential of me duplicating an outcome. Okay? Does that make sense, everybody? So that's kind of a tabular way of developing a sample space. Okay? And that's a good technique when you're doing maybe 2 things back to back, 2 maybe rolls or 2 pulls of a card or something like that. Maybe we could do the same thing with maybe I roll a dice and then pick a card out. Okay, so I could roll a 1 and then I pair that with maybe all 52 cards, and then I roll a 2 and pair that with all 52 cards. Does that make sense? And then that would be a pain in the butt to look at that chart and develop that chart, but that would allow me to develop a sample space. Okay. Now what we would do is ask, okay, now that I've got my sample space, now I've got an understanding of what my denominator needs to be. Because your denominator is always your sample space. It's all possible outcomes, right? Throughout all probability that we've talked about this year, last year, year before, whatever, your denominator is all potential things that could have happened. So you got 36 things here that could happen, right? So that's my denominator. If my sample space is wrong, then my whole probability is wrong, right? So in my opinion, that's the first thing that we should determine. What's your sample space look like? Because if you got the denominator wrong, it doesn't matter how accurate your numerator is. Your quotient is going to be incorrect. Okay? So, if I ask you now what's the probability of rolling a sum of 12, how many of those outcomes sum to 12? Just 1, the bottom right one, right? Okay, so 6, 6. So you have 1 out of 36, right? Okay? If I would have had the wrong sample space, let's say I create a sample space that only has 30 outcomes in it, and I have 1 out of 30. Is that a wrong probability? Yeah. Okay? Because I have the wrong sample space. I need the 36 for my sample space, right? Okay? Questions on that? Does that make sense? Okay? They'll ask all kinds of things here. They'll ask, what is the probability that the sum is greater than 6, or less than or equal to 5, or the product is greater than 20, or something like that. So you'd have to be able to do that little set of algebra. If I'm doing sums, I would add all these up, right? Add 1 and 1, add 1 and 2, add 1 and 3, add each one of these cells together. Okay? If I was going to do products, I'd set them all up together, and then check to see which ones are bigger than 20, which ones are less than or equal to 5, or whatever the question is asking. Does that make sense? We'll see questions like, we'll come back to this and investigate those types of questions later, but I want to make sure we understand sample space. Another common sample space that people are kind of on both ends of the spectrum with in regards to their understanding, I will ask questions about cards, and I'll get some people to be able to, tell me every single relationship between in the deck of cards. They tell me all the, what are those called, ace, diamond, the suits, okay? You tell me that you got, that top one's clubs, the second one is spades, third one's hearts, fourth one's diamonds, right? Okay. No. You got 3 face cards. You got the jack, the king, and the queen. You've got aces, and then 2 through 10, right? Some people have never seen that before. Okay. When a lot of our probability questions in the process of writing textbooks and stuff like that was first conducted, technology was very limited. They didn't have cell phones. They didn't have TVs and stuff like that. The common thing to do was play cards. So it's common knowledge. Everybody knew what a deck of cards looks like, right? I guarantee you have friends that don't have a clue what a deck of cards is. Okay? So I need to make sure that we understand this sample space because some of your questions are going to be targeted towards this. All right? And that's to build an understanding of just simple probability. Your questions on your end of course exam are not going to be, and I would be surprised if they are, what's the probability of picking out a jack out of a deck of cards? Or what's the probability of picking a red jack out of a deck of cards? That's not going to happen. But in order to get to a point where we can address the type of questions that are going to happen, we need to start here and understand this and understand sample spaces. Okay? Does that make sense? So they'll ask you things like this. Let's just do one real quick. And this is the benefit of knowing what your sample space looks like. If I were to ask you this question without this picture, if I say what's the probability of picking a 3 or a diamond, without a picture, that's a hard question to ask. Okay? How many 3s are there? 4. 4? So 4 out of 52, right, would be 3s? When I say or, okay, the word or for us in probability refers to addition. Okay? It means that you have additional objects that should be existing inside your favorable outcomes. Does that make sense? Okay, so the fact that it was a 3 said that you have 4 favorable outcomes. The fact that it's a diamond, how many favorable outcomes align with a diamond? 13. Okay? So now here's the thing. Because the word or, so I would succeed in this probability if I had a 3 pulled out or a diamond pulled out, right? How many things then are there that are a 3 or a diamond? Okay, so the number one wrong answer is 17. Why is that the number one wrong answer? Okay, so that's where understanding your sample space becomes beneficial. When I look at my sample space here, the question was a 3 or a diamond, right? So let's highlight the 3s. So there's your 3s, right? And those got counted in the 4 out of 52, correct? Then if I highlight the diamonds got right here, right? Those got counted in the 13 out of 52, correct? What was special about that one right there? It got counted twice, correct? It was in the 4 out of 52, and it was in the 13 out of 52. You can't have it in there twice because now it makes it unequally likely to occur. So we need to remove it once. And without seeing that overlap and understanding my sample space, it might not be all that obvious to realize that it's in there 2 times. Okay? Does that make sense? Understanding your sample space is critical. Okay? Let's say we've got this situation. And it doesn't matter. The scenario I've got here is first child, second child, third child, and we're talking about whether they're going to be boys or girls when they're born. Okay? So I want to know what is the structure of this family. Okay? When we do this, it doesn't have to be boys and girls. It could be heads and tails. It could just be anything that has kind of 2 possible outcomes. Okay? We could really set this up with. You guys remember questions where, like, Susie has 3 pairs of shoes, 4 pairs of pants, and 5 tops? Do you know how many different outcomes that you can make, and how many different outfits you can make? You take 3 shoes times 4 pants times 5 shirts, and that tells you how many outcomes you can make, how many outfits you can make, right? Do you remember what that's called? Fundamental counting principle. Okay? So, here's the idea. This is the same thing. If I have my first child, how many options do I have in regards to boy or girl?
2.
2. If I have a second child, how many options could be there? 2. Third child? 2. If I multiply those,
8.
I get 8 total outcomes. So there could be 8 different configurations of boy, boy, girl, boy, 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 girl, boy. 8 different structures of how the children in my family align in regards to boy and girl and ultimately first, second, or third. Does that make sense? So now here's the thing. You can do this maybe writing, so I could have all boys, right? I could have all girls, right? Why not? Somebody said no. Can I have, if I have 3 children, can they go all the girls? Yeah. Okay. Could I have 2 boys and a girl? Can I have 2 boys and a girl be in the middle? Okay. So here's the idea. I could keep doing this. But when I'm doing this, it's going to be really hard for me to realize that, especially if I didn't understand accounting, the fundamental accounting principle, I'm going to have 8 outcomes. It's going to be really hard to realize and recognize whether I've repeated one on accident. Does that make sense? Or if I've left one out on accident. So what we come up with is what we call a tree diagram. Okay? A tree diagram, by definition, is a series of segments that emanate from a starting point that is used to identify all the possible outcomes in a probability situation. Okay? 13. Okay, so here's what we do. We start from an initial point, and we draw branches of our tree out to our first potential situation. And our first child could be a boy or a girl, correct? If we have a boy under our first child, what's my option for a second child? Boy or a girl. If I had a girl as my first child, what's the options for a second child? Boy again or girl. If I went boy, boy, third child could be boy or a girl. If I go boy, girl, third child could be boy, girl. And I'm hoping you get the idea here. Now, the benefit of this is ultimately kind of realized when we go like a 4th child and a 5th child, or we maybe have more than just 2 options per child or per scenario here. But what we realize then is if we start back here and follow the branches of that tree, that provides us one outcome. We could have boy, boy, boy in our family, right? If I go back and go boy, boy to girl, right? So boy, boy to girl could be a second outcome. And that's going to be boy, girl, boy. Boy, girl, boy. Now what I need you to understand is that one and that one are different. Even though it's 2 boys and a girl, right? And that top one, the girl is the youngest. And the bottom one, the girl is the middle child. That's a different structure for the family, right? Okay. Continuing through this pattern, I get boy, girl, girl. Boy, girl, girl. Boy, girl, girl. And this bottom one, girl, boy, boy. I could go girl, boy, girl. Girl, girl, boy. And a family similar to Dalton's, girl, girl, girl. All right. So, how many outcomes we got here?
8.
We got 8 outcomes. Makes sense. 2 times 2 times 2, right?
Yep.
Now, the questions that they will ask then is what is the probability that you have all boys?
1 out of 8.
1 out of 8. Okay? Now, I could have known that 8 without the tree, correct?
Yeah.
Would it have been hard to know that 1 without understanding what my sample space looks like? Yeah. Okay? Now, they could ask the question, what's the probability of having all the same gender?
2.
So that'd be 2 out of 8, right? It could be all girls, or they could all be all boys. Okay? So 2 out of 8 would be 1/4. Okay? Let's kind of draw a comparison, because another common question they ask then is this scenario. You're going to flip a coin.
Oh my God.
Okay? And they want to know what's the probability that you, in 3 flips, that you get heads, heads, heads. Well, think about this.
Flip it 3 times, you got 1 out of 8.
Can I just say that this is a flip instead of a child?
No.
And now on the first flip, I can get heads or tails, right? And the second shot, I get heads. Or sorry, second flip, heads or tails. This could be heads or tails, right?
I think it works like that.
All right, so heads, tails, heads, tails, heads, tails, heads, tails. Now, if I go through and write this set of outcomes, how many of them are heads, heads, heads? Only one. Okay, 1 out of 8, right? So it's a different noun. Not using children, I'm using heads and tails now, right? But it's the same idea to set up that sample space. Okay. Now here's the question. If I asked you to do this, let's say I give you all a coin, and I tell you flip it 3 times and record what you have flipped after 3 times. Does that make sense? So flip it 3 times and see, was it heads, tails, tails? Write down heads, heads, tails, heads, 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 tails, heads, heads, that kind of thing, right? If you do that 8 times, what this is saying is that one of those 8 times will be heads, heads, heads. One of those 8 times will be tails, tails, tails. One of those 8 times will be heads, tails, heads. But if you do that, will that really happen?
Not always.
Not necessarily. Okay? So that idea is that 1 out of 8, I should get heads, heads, heads. 1 out of every 8 times I do this. That is called theoretical or empirical probability. Okay? Actually doing it and recognizing how many heads, heads, heads I get, that's called experimental probability, right? Yes. Does anybody know how they're linked? Okay, if it's a big enough sample space. So the idea is, let's, because this is a little bit, I think, confusing to think about. Let's just do heads and tails. If I give you all 1 quarter, and I tell you to flip it, okay? Let's say I tell you to flip it 5 times. Are any of you, this reason I chose 5, are any of you going to get 2.5 heads, 2.5 tails?
Yeah.
You can't. You can't. You're going to get either 2 heads, 3 tails, 3 tails, 2 heads. Might have been the same thing. You might get 1 head, 4 tails. You might get 0 heads, 5 tails, right? Okay? So none of you are going to get the 50-50. You're not going to land on the plane. You're not going to land that way. Okay? So when we deal with probability in that nature, if you have a small sample space, so each one has a small sample space of 5 flips, right? Some of you might get 20% heads. Some of you might get 40% heads. Some of you might get 10% heads, right? If I were then to ask you to do it 10 times, and then 20 times, and then 30 times, individually, your probabilities of getting heads or tails are going to eventually merge to 50%. Okay? Now, you might still flip it 30 times, and you might be the person who gets 25 heads and 5 tails. That happens. But if I ask each one of you to do it 100 times, okay, and then we take all of our results and put them together, we'd have about 2,000 sample space events. Does that make sense? You're going to have really close to 1,000 heads and 1,000 tails on a sample space. Okay? And even more that you do, the larger the sample space you have, the more your experimental probability will align itself with the theoretical or empirical probability. Okay? So the larger the sample space is, the more likely your probability in your experiment is going to match it. That's why when we do studies, and you see this on pharmaceuticals all the time and commercials, they will tell you at the bottom of the screen, for that drug, how many people were in this study. Because if there were 20 people in this study for this new drug that came out, and it only helped 80% of them, with 80% of 20, 16, I'm not really all that confident in going and taking that drug. Does that make sense? Okay? But if my sample space says, we researched and we did our experiment on 10,000 people, and it impacted 80% of those effectively, then maybe I feel a little more comfortable about taking that drug and fixing my ailment. Does that make sense? Okay? So, those are all things to kind of think about when we talk about probability. But experimental and theoretical probability start to align themselves, match to one another the more objects you have in your sample space in your experiment. Okay? If we have time tomorrow, I've got a simulation that I can show you to kind of explain that or recognize that. All right, here it says an event. An event consists of a probability experiment, or the outcomes of a probability experiment. We talked about this in chapter 10. Okay? An event is the idea of what's the probability of getting heads, what's the probability of getting tails, what's the probability of getting boy, 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 or probability of getting boy, girl, boy. All of those heads or tails or boy, girl, boy, those are events. Those are things that could happen, right? Okay? When we talk about probability, this is the way that most textbooks are going to define probability for you. They're going to say N, and then put in parentheses capital E. Capital E represents the events, and N out front like this, it's a notation to say the number of events. Okay? And really what this object here is, number of outcomes matching the events. Okay? If you think back to what we did in chapter 10, another way of saying that is favorable outcomes. And remember that? Numerator is always favorable outcomes. The number of outcomes matching your events, or more concisely, N of E. Okay? That bottom, if you remember back to chapter 10, it was total possible outcomes, right? Or total possible area when we were working in chapter 10. What do you think that S stands for here? Number of what? Number of objects in your sample space. The S stands for sample space. But again, if you want to go on more of a layman's terms of writing your formula here, you can write number of total outcomes. Or if you want to just say sample space, okay, down at the bottom. You're going to see your formula for probability written over and over several different times. And there's going to be different notations. For instance, we'll show you frequency distributions tomorrow. And we get probability of an event and a frequency distribution being the frequency of a class divided by the total frequency and distribution. F over N. Well, what that F stands for is favorable outcomes. N talks about your sample space. Total number of things that could happen. It's always the same. There's just different ways that they're going to describe it in regards to different situations in regards to probability. Okay? Questions on that? Okay? Numerator is the number of events, or number of outcomes aligned with your events, and the denominator is always your number of objects in your sample space. All right? So let's do a couple quick ones here. And again, these are questions that are not going to be asked on the end course again. They want to know probability of getting a jack. They would have asked that to you in the 7th grade or 8th grade. How many jacks are there in deck cards? 4. How many numbers or objects are in your sample space? 52. So 4 divided by 52, right? Now, something we do with probability is that we always reduce. So 1/13, right? Meaning then, if I were to give you a deck of cards, lay them out in front of you, and I told you to flip over 13 of them, it's saying that one of them is going to be a what? A jack. Will that necessarily happen? No, but that's the theory. That's what we're saying is supposed to happen. Does that make sense, everybody? Okay. Part B says, getting the 6 of clubs. There's only 1 6 of clubs, right? Another way of saying that is that you're going to get a 6 and a club within one draw. A 6 and a club within one draw. Well, there's only one card that satisfies that set of conditions, right? So 1 out of 52. Do the last one. Getting a 3 or a 6. How many 3s are there? There's 4. How many 6s are there? 4, right? So remember, our numerator has to be favorable outcomes. Numerator has to be the number of things that are aligned with getting a 3 or 6. There are 4 3s, there are 4 6s, so 8 different things will match that event, right? And how many do I get to choose from? 52, so 8 out of 52 is 2 13s. Okay? So we're saying that if I gave you 52 cards, and I told you to turn over 13 of them, this is saying 2 of them are going to be 3s and or 6s. So you might have 1 3 and 1 6. You might have 2 3s and 0 6. You might have 2 6s and 0 3s. that make sense? Okay? Not necessarily going to happen, but it could. Did we do this one here? Did we do C? Well, we did the one where they're overlapping and there was one counted in there twice? Okay. Sometimes my classes kind of, in my mind, run together. All right, so let's do probability rules. These are the 4 rules that kind of set the premise for all probability. And they're pretty easy. You already know them. Okay? The probability of any event occurring is between 0 and 1, inclusive, meaning we could have a 0 probability and we could have a probability of 1. Okay? So all probabilities are going to be between 0 and 1. A lot of times we're going to write them as decimals, and you see them on the end of course exam a lot of times as decimals. Okay? But I think on the end of course exam they often will accept, like you type in like 60%, they would have also accepted like 0.6, or they would have accepted 6 over 10. Okay? Or 60 over 100, or 600 over 1,000. They'll accept all different versions of 60%. Okay? Probability rule number 2 says, well, what happens when your probability event is equal to 0? What do we say that's it's impossible to occur. Okay? It's not going to happen. Okay? Probability of an event not happening is always 0. Okay? Probability that any event is equal to 1 means the event is certain to happen, sure to happen, or guaranteed to happen. Okay? Or if you talk to Dalton, it's sure to happen, like the ocean. All right, and this last probability rule actually allows us to generate an idea here in a moment, but it says that the sum of all probabilities is equal to 1. Inside a particular experiment, all my probabilities should add up to give me 1. So here's the idea of that. Let's go with, what's the probability of getting an ace? 4 out of 52. Okay? What is the probability of getting not an ace? Okay, 48 out of 52. And here's the idea. If I think about ace and not an ace, does that encompass my entire sample space? Yeah, if you lay your aces out, you got 4 of them. If you lay out not your aces, you got 48 cards there, and that will make up your entire deck, right? So this is saying the probability of an ace, with this rule here that I've highlighted, it is saying the probability of an ace plus the probability of not an ace should equal 1. Does 4 50-seconds plus 48 50-seconds equal 1? Yes. Yes. Now here's the thing that I think is difficult, because sometimes, and this situation doesn't necessarily exist here, but it is kind of a pain in the butt. If I didn't know maybe how many aces I had, and they ask you what's the probability of not an ace, I would have to look at my sample space and go through and count all the cards that are not aces, right? And I have to count 48 things. Okay? Where if I do something like this, if I say, I'm interested in finding the probability of not an ace, isn't this an equation right here up top? Is that an equation? So we're going to subtract the same thing from both sides. So if I want to find the probability of not an ace, and I want to be lazy about it, I don't want to go through and count all 48 things, can I say the probability of not an ace is equal to 1 minus the probability of an ace? 1, is that 52 over 52? What's 52 over 52 minus 4 over 52? 48 over 52. Is that the same thing as what we knew there by looking at our sample space? There will be times, guys, where it is impossible for you, because you don't have the sample space in front of you, or you don't have a good understanding of the sample space, it will be impossible for you to figure out the probability of something occurring. But you can very easily find the possibility of it not occurring. And because you know the possibility of it not occurring, you automatically know the possibility of it occurring. Does that make sense? Okay. That idea is referred to as the complement of an event. Okay. The complement of an event is a set of outcomes in the sample space that are not included in the outcomes of the event E. Okay? Complement of an event is a set of outcomes in the sample space that are not included in the outcomes of event E. So if event E was the probability of an ace, The probability of not an ace is a complement, right? It's essentially the way I structure it in kind of non-mathematical terms is that a complement of something is everything else. Talk about complementary angles real quick. What do they add up to? Not 90. 90. If I tell you one angle is 30, what's the other one? 60. It's everything else that got me to the total of 90, right? Okay? So you've seen this word complement before in regards to angles. It's the same thing here. Complement means it's everything else. Okay? So if I say you guys as a group are a sample space, and I cut out this first row, who's the complement to that first row? Yeah, rows 2, 3, and 4, right? Okay? So the complement is everything else. And these three formulas they're all the same thing. This one here, this last one, is the fact that the sum of all probabilities is equal to 1. So the probability of an event plus the probability of the complement of that event should equal 1. And then if I solve that formula for P of E or P of E bar, I will get those other two equations. Okay? Now when we talk about complements, a lot of times we use this notation. So E is the probability of the event. If I go E bar, that is the complement. Okay? So if I wanted to say a probability, you usually don't do this if you've got words to express a event. If I say a probability of a face, if I do something like this, okay, that would be a non-face, right? We call that face bar. That's the complement of faces, okay? But usually if we've got words to identify face, then we can say non-face to identify the complement, right? If we look at some objects, actually some examples down here at the bottom, give me I don't want the probabilities, but if I rolled a 4, what's the complement of rolling a 4? Okay, so the probability is 5 out of 6, but the complement is 1, 2, 3, 5, and 6, isn't it? Does that make sense? So 4 is the event. That would be E. This here would be E bar. Okay? Selecting a letter of the alphabet and getting a vowel. What would be the complement of getting a vowel? Well, 8. So let's count 1. But I don't want the number. I don't want the numerical result. I want you to verbally tell me what we would be looking for in the complement. Okay, what was it called? Consonants, right? So the complement of vowels is consonants, right? The complement of even numbers is odd numbers. The complement of positive numbers is negatives, right? Does that kind of make sense to everybody? Okay? So everything else. So here's the idea. If I wanted to find the probability of getting a consonant, I would have to go through the alphabet, 26 letters, and say, okay, B, C, D, F, G, H, J, K, L, M, N, P, Q, R, S, T, V, W, X, Z. Right? How many did I count? Counted 20. Okay? So, would you agree that listing the alphabet and counting which ones are consonants is a pain in the butt? What if I did this? What if I said probability of a vowel? How many vowels are there? A, E, I, O, U. Let's count Y. 6 out of 26, right? That's probability of getting a vowel. So what's the probability of getting a consonant? 20 out of 26. You see how getting the consonant probability through the use of getting the probability of a vowel is easier? You don't have to count then, right? Okay? That's why we use that complement concept a lot. Selecting a month and getting a month that starts with a J. What's the complement of that? It'd be 9. There's 3 months, January, June, and July, that start with a J, right? So the complement would be February, March, April, May, August, September, October, November, December, right? Okay. You don't know that? By selecting the day of the week and getting a weekday. So what's the complement of a weekday? Weekend, so Saturday or Sunday, right? Okay. So those are the complement ideas, and that's going to be important for us as we move on through some of these questions that we'll see later in the week. Some of them you have to use the complement idea to find your probabilities.